Welcome to QSTI Prep Academy. Today's explainer is all about giving you the overall important view of EPA Method 2D. I'm so pumped you've joined us because if you're gearing up for that QSTI exam, mastering these EPA methods is absolutely essential. Today, we're putting a laser focus on Method 2D, which is your go-to for measuring gas volume flow rates. We're going to break down the source text, look at the precise equipment specs, and completely unpack the procedures and formulas you're definitely going to be tested on. So grab your notebooks, get comfortable, and let's crush this material together. Here's our quick roadmap for today's masterclass. We'll start with Welcome to Method 2D, then hit our equipment and safety check, take a quick QST Academy study break, run through the data collection procedures, dive into the Method 2D formulas, and wrap it all up with quality control and summary. All right, Section 1, Welcome to Method 2D. So what exactly is Method 2D, and when are you actually supposed to use it out in the field? Well, the absolutely critical thing to remember for your exam is that Method 2D focuses specifically on small pipes and ducts. Basically, all the gas flow in that pipe or duct gets directed through a device to measure the flow rate or pressure drop. But listen up, because here is a massive caveat straight from the EPA guidelines. You need to use extreme caution if you're applying this to intermittent or variable gas flows. Why? Because the calibration of your devices will be heavily thrown off by fluctuations in stat gas temperature, pressure, and molecular weight. The whole point here, the main data quality objective, is that strictly following this method seriously enhances the quality of data you get from all your subsequent air pollutant sampling methods. It's the foundation, right? Moving right along to Section 2, our equipment and safety check. Okay, so what gear do we actually need to make these measurements accurately? Grab a pen, because knowing your equipment tolerances is a massive target for exam questions. First, your critical tools start with a gas metering device. Think a rotameter, an orifice plate, or something similar. This device absolutely must be capable of measuring the stack flow rate to within plus or minus 5%. On top of that, it needs a temperature gauge accurate to within plus or minus 2% of the minimum absolute stack temperature, and a pressure gauge accurate to within plus or minus 5 millimeters of mercury. You're also going to need a barometer that's calibrated against a mercury or NIST traceable barometer, and a simple stopwatch that measures to within 1 single second. And hey, when you're picking your metering device, you've got to make sure its capacity can handle both your expected maximum and minimum flow rates, factoring in things like molecular weight, dew point, corrosive characteristics, and your specific pipe size. Now, please keep in mind that this method involves hazardous materials and operations. The EPA text explicitly points out that it doesn't cover all the safety problems associated with its use. So, establishing your safety and health practices before testing is an absolute must. It is 100% on you, the user out in the field, to make sure these safety protocols are completely locked down before you take a single measurement. No cutting corners here. All right, Section 3, time for a quick QSTI Academy study break. You guys are doing great. Hey, please subscribe to our channel so you never miss an explainer. And look, if you want to pass the QCNTSDI exam, just send an email to qcntsdprepacademy@gmail.com. We're here to help you nail that certification. Okay, break's over. Let's jump back into the technical details. Getting back into it with Section 4, data collection procedures. So once our leak checks are good to go and our equipment is totally dialed in, how do we actually collect the volume rate measurement data? Well, it depends slightly on your flow type. For continuous, steady flow, you have to record your metering device flow rate or pressure drop rating along with temperature and pressure at least once an hour. Plus, you're required to take a minimum of 12 equally spaced readings of each parameter during your test period. Don't forget to grab your barometric pressure at both the start and the end of the test. Now, what if your flow is non-continuous or non-steady? Like we said earlier, use caution here. You'll follow the same basic steps, but you have to record the parameters on a time interval frequent enough to properly profile each cyclical or non-continuous event. Thankfully, the method does let you use a multi-channel continuous recorder to make your life a whole lot easier. Which brings us to Section 5, the Method 2D formulas. Okay, the real make-or-break point of this entire method comes down to the math. Collecting data is only half the battle, right? Calculating the standard conditions is where you really prove your mettle. Watch this write out carefully on screen. This is equation 2D-1, and it's what you use to find your gas flow rate by balancing the test meter volume with absolute temps and pressures. Let's break down the variables quickly so you understand exactly what's happening. QS is what we're solving for. K1 is a constant, specifically 0.3855 degrees Kelvin per millimeter of mercury for metric units, or 17.65 degrees Rankine per inch of mercury for English units. Ym is your test meter calibration coefficient, and Qm is your test meter volume flow rate reading. You multiply that by the sum of P bar, your barometric pressure, and PM, the test meter average static pressure. Finally, divide all of that by Tm, which is the absolute test meter average temperature. You've got to understand how these variables interact to correct your volumetric flow rates. It's a fundamental requirement for the exam. And now, check out this next one coming to life on the screen. This is equation 2D-2, and you'll use this to calculate your test metering device calibration coefficient, Ym, against a standard reference meter. Ideally, you want to calibrate in the field with the actual principal stat gas you're metering, like air or nitrogen. A calibrated dry gas meter is totally acceptable as a reference here. So, QR is your reference meter volume flow rate reading, and TR is the absolute reference meter average temperature. Multiply those by the barometric pressure. Then divide that whole top part by Qm times Tm times the sum of the barometric pressure and the test meter average static pressure. This QA measure is exactly what ensures your final flow rate measurements are actually accurate.
Finally, Section 6, Quality Control and Summating.
To actually guarantee high-quality data in the field, we rely on frameworks like this one. This is based straight on Figure 2D1 from the EPA docs, the volume flow rate measurement datasheet. When you're out there taking those 12 equally spaced readings, this is your blueprint. At the top, you track the plant, date, run number, and sample location. You log barometric pressure at the beginning and the end. Then, row by row, systematically, you document the time, flow rate reading, static pressure, and temperature in both Celsius or Fahrenheit, plus its absolute equivalent in Kelvin or Rankine. At the very bottom, you crunch the averages. Honestly, keeping this data rigorously organized is literally just as important as the physical measurements themselves. So, having walked through the specific scope for small pipes and ducts, the strict equipment tolerances, the collection rules, and watching those critical equations get drawn out, do you feel ready to conquer Method 2D on your QST exam? Review these parameters, get those formulas locked in your memory, and you're going to do absolutely fine. Thanks so much for hanging out with us for this explainer, and we will catch you in the next masterclass.